All right, before we move into the next concept, we're going to and it's really just an extension of what we've learned so far. So we're going to review quickly what we talked about in the last lesson um, about a function and its derivative. So if the derivative is equal to 0, then f of x will have a horizontal tangent line. Please keep in mind that we talked about that doesn't necessarily mean it's going to be a maximum or a minimum. We looked at that. We looked at several graphs where that wasn't the case. We could have a horizontal tangent line, and it doesn't need to be a relative maximum or minimum. So when the derivative is equal to 0, it just means I know that I have a horizontal tangent line there. I'm not going to make any conclusions about extrema at that point. When the derivative is bigger than 0, then f of x is increasing. Again, just review stuff from before. When f prime of x is less than 0, then f of x is decreasing. Now what we can say is if f prime of x changes from positive to negative, so when our derivative changes sign, that's when we can say f of x has a relative maximum. And we're going to want to show first, before we even do that, is that the derivative there, f prime of x, is actually equal to 0. So we've got our horizontal tangent line. Then we'll decide, is it a maximum or minimum based on when it changes. What's the sign change on the derivative? So if we look at the derivative changing from negative to positive, then we know f of x is going to have a relative minimum. Using some of those ideas, using some of these ideas, now we haven't really looked at it graphically. We've just talked about numerically and with the equation how that happens, what's happening there. Let's look at the graph. If I give you, this will be definitely a question you're going to come across. If I give you the graph of f of x, could you sketch a possible graph of f prime of x and vice versa? So I think the easiest way to kind of do this is when we look at the graph of f of x, we're looking for any spots, any x values where I have a horizontal tangent line. So in this graph, we've got a polynomial, and it's got 3 relative extrema, and those look to be the only places where I've got a horizontal tangent line. It seems to occur at an x value of -4. So I know that if the tangent line is horizontal, the slope of that line is going to be 0. And that's what the derivative represents. The next relative extrema, we have a relative minimum at an x value of 1. So I'm going to plot on my graph of the derivative, I'm going to plot 0 at an x value of 1. And then again, we have a relative maximum at x equals 5, it looks like. So on the graph of the derivative, I'm going to plot 0 because that is the slope of the tangent line on the graph. So remember, a y value on the graph of the derivative is representing what's the slope of the tangent line or the slope of the graph of f. So that's where we're going to start. That kind of breaks our x-axis or our number line into 3 intervals here. We've got a pink interval. We've got this tan interval. Sorry, 4 intervals. 3 points break a line into 4 segments. 2 segments in the right, 2 rays. And we've got this white interval. So we now have these intervals, and we want to kind of describe, find out what's happening over those intervals on f prime. So in the pink interval, from -infinity to -4, we kind of know what's happening with the derivative, because if we look on f is increasing, and we talked about this in the last lesson. Whenever f is increasing, then we know f prime is positive. So I know on this pink interval, I'm going to graph this thing in green, that the derivative has to be positive or above the x-axis. All those y values are positive, indicating positive slopes of tangent lines. All right? We also know it's a polynomial, so there's other advantages we have here with polynomials. I can tell that my f of x looks to be like a power of 4. It's got 3 terms. So the graph of f prime should have one less turn. It should be one less degree because that's how power rule works. You lower the degree by one. All right, so on the next interval, this tanish interval, actually I'm going to make these match. So on that interval, that was pink, so we were saying that f was increasing. Now we're on that tanish interval. What's f doing? F is going down or decreasing. So over here on my graph of my derivative, I need to be negative, but then I have to come back to 0, and it's a polynomial, so maybe it does that. So on the tan interval, you can see all my y values on my derivative are negative. If I go for my purple interval, or blue, f increases again. So then over here on my derivative, those y values all have to be positive. And then when the function starts decreasing again on that white interval, then I see that my derivative has to be negative and have negative y values. Okay, so that's where we can that's how we can sketch a possible graph of f prime. We don't quite know on f prime how high or how low those extrema go, but we're just looking to sketch to have an idea of what it might look like. We definitely know when it's going to be positive, when it's going to be negative, when it's going to be equal to 0. All right? Taking some of these ideas, we're given a graph and we're asked questions about the graph. Now, we are given the graph of f here, and we're asked questions about f prime. So first of all, it's asking us about f prime at 4. So remember it says to approximate. That means if it's asking us to approximate, we're probably going to use a secant line slope. If they wanted the exact one, we can do the derivative, but we don't have an equation for f. So we have to use a secant line to approximate the value of the derivative at 4. So we're at 1, 2, 3, 4. So that is a point that's not indicated on this graph. It's looks to be right about there. But we do have other points on the graph on either side of it. So we're going to use the point 3, -1 and the point 5, 4 to approximate the slope of the tangent line by doing the slope of the secant line of the points on either side. So if I kind of draw this in, that's the slope of our tangent line. If I draw the secant line, you can tell for this graph, the slope of that purple secant line is going to be a pretty good approximation for the slope of the tangent line. So we've got to watch out for this whole approximate idea, whether they ask for the derivative or approximate the derivative. So we're going to do to approximate f prime of 4. It's going to be about, and we're going to do our slope formula. I'm not going to talk you through it. We're going to get about 2.5 there. At what values of x is the derivative 0? Based on the graph of f. So derivative 0 means we've got horizontal tangent lines. It looks like one turns up there, one turns up there, and one turns up there. So we're going to say that f prime of x, I hate when this starts getting skippy like this, f prime of x equals 0 when x equals -4, 1, and 5. Justify your answer because the graph of f of x has horizontal tangent lines at those x values. Okay, on what open intervals is the derivative less than 0? So that is speak for negative and justify your answer. Well, when is the derivative going to be negative? That means when's the slope of this graph going to be negative? And you can use tangent lines to visualize that. So if I look for areas at some points along the curve here, if I draw these tangent lines, no, the slopes over there are positive. It looks to be just here, which we kind of learned the other day. It's on these intervals here where f is decreasing, then I know its rate of change or its derivative is negative. So we're going to say f prime of x is less than 0 on the interval negative 4 to 1, union 5 to infinity, because f of x is decreasing on those intervals. On what open intervals is f prime of x bigger than 0? Justify your answer. I'm not going to do that one with you. It's vice versa idea. You guys can figure that out. That'll cut down our video a little bit. Okay, you're going to look on the graph and do the opposite idea. At what values of x does the graph of f prime of x go from being below the x-axis to above the x-axis? Justify your answer. So f prime of x going from below the x-axis means it's negative, to above the x-axis to positive is going to be any spots where my function changes from, if I'm below the x-axis on the derivative, it's negative, so the function was going down. So it's going to be anywhere the function switches from going from decreasing back to increasing. Right? So that looks like here my derivatives are negative, and then this is f, right? So then as I turn around and start going up again, my derivatives will change to positive. And that's what they're asking me. Below the x-axis is negative derivatives. Above is positive derivatives. So we're going to say that f prime of x will go from positive. I'm not going to say above the x-axis, even though I should restate the question. That's good practice for the AP exam. We'll go from positive to negative. Oh, I'm sorry. It was the other way around for this one. We're starting below the x-axis. From negative to positive when f of x changes from decreasing to increasing at x equals 1. I shouldn't say go from. I should say f prime of x will, I could also say change there. Changes from. Okay? Now we look at the last one. It's vice versa again. I'm not going to go through that one with you. Let's look at a second example. Here now we're given the graph of the derivative, and we're asked questions about f. So on what open interval is the graph of f of x increasing? Justify your reasoning. So f will be increasing anytime the derivative is positive. So I'm going to look on this graph and try to identify when the derivative is above the x-axis. So we're going to say that we can see it's there. So we're going to say that f of x is increasing when f prime of x is above 0 or positive, which occurs on the interval. Oh, my pencil died. Hold on. Paused the video and charged it. My pencil's alive again. Occurs on the interval -3 to -2, I think it was. On what open interval is the graph of f of x decreasing? Justify your answer. Vice versa. There is an interesting thing to note here. The interval will be these open intervals. I'm excluding the point 2 because at 2, the derivative is 0, which means the function's neither increasing nor decreasing. This will depend on the instructor you talk to sometimes. That's why we didn't include -3. At -3, the function's not decreasing. The definition I like of decreasing is if you look a little bit to the left, that y value, I got to mute that, sorry. If you look a little to the left of a point to define it as decreasing, the y value is going to be slightly higher. And if you look a little bit to the right, that y value is going to be slightly lower. So at -3, we can't look a little to the left, so it doesn't fit my definition. Same thing happens at 2. If I go a little bit left, the y value is slightly lower. A little bit to the right, the y value is also slightly lower, so it can't be increasing or decreasing. So we have to exclude that point. It's the derivative is positive. Is negative on all of these points, but I can't put 2 in there. Right? It's not negative. It's 0. At what values of x does the graph of f have a horizontal tangent line? Justify your answer. Anywhere the derivative is 0, that means the tangent line must have gotten horizontal. So that happens twice. F of x has a horizontal tangent when f prime of x equals 0, which occurs at x equals -2 and x equals 2. At what values of x does the graph have a relative maximum? Justify your answer. Maximum is where they equal 0 is potentially a maximum, but it also has to switch. The derivative has to, I can't say it, no pronouns. The derivative has to switch from positive to negative, and then that means the original function would have switched from increasing to decreasing, which is a maximum. So we're going to say that f of x has a relative maximum when f prime of x changes from positive to negative, which occurs at x equals -2. Right? That's right here. The derivative switches from positive to negative. Again, this will be the vice versa idea. We want the derivative to switch from negative to positive. It does not happen on this graph. Here, our derivative is negative. It gets to 0, but then it stays negative. So on f at that point, what could have been happening is that on the graph here at 2 of the original, I don't know what it looks like, but if it was decreasing, flattens out for an instant and keeps decreasing, that could be a spot like we saw the other day where we have a horizontal tangent line at 2. So maybe that's what's going on there. That's how your derivative can be negative, get to 0, and then stay negative afterwards, right? These tangent lines here are all negative approaching. It flattens out to a 0 derivative, and then it goes back to negative on the other side. What is the slope of the normal line to the graph of f of x at x equals 4? So they're asking about f, okay? The slope of the normal line of f. I don't have a graph of f. I have a graph of f prime. So at 4, if I go find the y value on f prime, I get -2. So I know that f prime of 4 is -2. So this means the slope of the tangent line at x equals 4 is -2. And then we know the slope of the normal line is the opposite reciprocal. Look, I'm talking. I could just say this stuff. Why am I writing it all down? Because it asks you to justify your reasoning. You have to write this down when you're trying to explain stuff. You can't just assume they know stuff. Is the opposite reciprocal. Oh, God, I can't spell that. That's a problem. There's an R in there. Okay? I just do that, and then you never really know if I spelled it right or wrong, or I can just move on. Is the opposite reciprocal. So the slope is, I want to say the slope of the normal line. You could probably say it more succinctly than this. 1/2. All right, let's move on. So here's some questions that you're going to see for sure. For each of the given functions, I don't think I'm going to do both of them. I think I'm going to do one because we don't need to see both examples. For each of the given functions, determine the interval on which f of x is increasing and or decreasing. So we're given f, and they want to know when it's increasing or decreasing. They also want us to tell them any coordinates of relative extrema. That means any relative maximums or any relative minimums. And unless otherwise noted, perform the analysis on all values from negative infinity to infinity. Provide justification. So this is a big question, okay? And we see this one a lot. Over here you can see we have an interval just because of the cyclic nature of the sine function. So over here we're doing for all x values. All right, so first of all, since we're talking about when a function's increasing and decreasing, we need the derivative. It's easier trying to analyze when f is going up or down. It's actually easier to analyze when its derivative is positive and when it's negative. So if I take the derivative, instead of trying to figure out without a graph when this is decreasing, just for instance, I won't do decreasing, or I'll just say, okay, decreasing, increasing. Without a graph, trying to figure out the x values where that occurs, it's probably easier to analyze when its derivative is positive or negative. It's always easier to determine what intervals a function is positive or negative. So I'm going to analyze the derivative because it's an easier thing. So the first thing I think about is, well, if I want to know when a function is positive or negative, I should first find when it's neither. What x values is it neither positive nor negative? Okay, give me 1 second. My pencil's dying again. Okay, so when is it neither positive, the derivative neither positive or negative? When it's equal to, when the derivative is equal to 0. So to solve this, I'm going to factor out a 15x squared. So I get x squared minus 1. Can factor further. By the zero product property, I can say if a product equals 0, then each factor must equal 0. I solve those, I get x equals 0, x equals negative 1, and x equals 1. All right, so we're going to call those our critical values. Those are the values that we're analyzing our derivative. So now we're going to test our derivative. We're going to put those points in alphabetical order on the number line. We are testing our derivative, so we're going to label it as the derivative. So our y values, we want to test these y values. If these are the only spots where the y values are 0, that means on these sections, they must stick together because it's a polynomial. So all the y values for these x values must all be positive or all be negative. So we're going to test that. We're going to take one x value off of this, and let's say x equals negative 2. We are going to plug that into the derivative. We're going to say f of negative 2 is what kind of number? F prime, we're testing the derivative. I like my factored form to decide the type of number. I don't have to worry about this part because no matter what I plug in, that's going to be positive, so it's not going to affect the sign. So if I plug in a negative 2 into these other two factors and multiply them, what kind of number do I get? I get a negative times a negative is a positive. So I know that the derivative on that interval is positive. Now if I pick a number on this next interval, let's do like 0.5. F prime of negative 0.5, I should have said. If I plug that into my derivative, again, the 15x squared part's positive. I get a positive times a negative is going to give me a negative. So the derivative is negative on this interval. And I repeat a similar process. I'll choose 0.5 here. If I plug that into my derivative, I'm going to get a positive times a negative. I'm going to get a negative again. And then if I plug in 2 into our derivative, I'm going to get a positive times a positive is a positive. So it's much easier to do that, perform the analysis on the derivative. And now, based on all the stuff we've known, we could say, number one, we can make our statements about f of x. F of x is, I'll do the increasing first. Increasing on the intervals negative infinity to negative 1, union 1 to infinity, because the derivative is positive on those intervals. 2, vice versa. I'm not going to write it out. So I answered this question. Determine the intervals on which the function is increasing and decreasing.